Just trying to figure out how I get back to the waiting room if someone tries to enter. Okay, well. All right, well, let me start. So 2 weeks ago, I spoke about the following. There's a theorem of 1914 by a man named Kempner. And the title of his paper was A Curious Convergence Series. And he starts off by saying the following. You look at the harmonic series. It is well known the series diverges. The object of this note is to prove that if the denominators do not include all natural numbers, but only those which do not contain any figure 9, the series converges. So if you take this harmonic series, it diverges. But if you only sum over numbers which have no 9 in their decimal expansions, suddenly the series begins to converge. And he thought of this as curious. Let's see, I'll get this to a normal size. And more generally, the theorem says the following. So we're going to look at numbers written to base g. And for every integer g, fix g at least 2. Every positive integer has a unique geodetic representation. You write as the sum of digits times powers of g. And the digits are integers from 0 up to g minus 1. So if you just look at all the digits, all the integers whose geodetic representation has no digit c, again, the sum of the reciprocals of the numbers converges. And this is a quite lovely theorem. You find it in Hardy and Wright, which is the source of all things basic in number theory, I believe. And Hardy and Wright proves that this converges. Now, there was just a little ding, which might mean that someone is in the waiting room, but I can't figure out how to find the waiting room again. Actually, can't. Okay. So we want to generalize this, and there's a very nice way to represent the integers, which is a natural extension of the geodetic representation. And in this case, what you do is you take a sequence of a strictly increasing sequence of positive integers, G0, G1, G2, and so forth, where each number divides the next one in the sequence. So these integers, gi plus 1 over gi, well, they're integers because gi divides gi plus 1. And gi plus 1 is strictly bigger than gi, so this integer is at least 2. And every number is a sum of, you can write a term of this sequence, the gk's, as the product of these digits, of these d's. And every number has a unique representation in this form, summation ci gi, where ci is a digit between 0 and d sub I minus 1. Okay. So that is the what I call the script geodetic representation of an integer. And I just want to move on to what's more interesting. So this was a theorem that I discussed last week. If you take a geodetic sequence with bounded quotients, so gi plus 1 over gi is bounded by some number d. So for example, in the decimal representation, gi is just 10 to the power I, so these quotients are all equal to 10. In the binary representation, the g's are 1, 2, 4, 8, 16, and so forth, and the d's are all equal to 2. So we take this geodetic representation of the integer n, and we take I is a set of non-negative integers. Could be all the non-negative integers, but could be a proper subset. And for each I in the set capital I, we let ui be a non-empty proper subset of what would be the allowable digits. So the digit that multiplies gi, the ci, is some integer in this interval. And we take a subset of this set of digits. And you can think of them as the bad digits. And we look at all numbers, we let A be the set of all positive integers that have no bad digits. So whenever there's a I for which there's a restriction on what is possible for the digit C sub I, C sub I is always a good digit. It's not one of the elements of this UI. And so long as we have enough digits that are being considered, you know, that is, the set I isn't too small. And too small means roughly at least log k of the numbers up to k have some set of restricted digits. Then the set A of all these numbers that have no bad digits has density 0, and the harmonic series, the summation 1 over A converges. So that was the basic theorem from last week. Now, and there are some more theorems, all of which I'm going to ignore. So I want to get yeah, okay. So this week there's something new, and so what's new is the following. In the theorem of Kempner from 100 years ago, he looked at all the integers which had no 9s in their decimal representations. That was extended easily, and this is what is in Hardy and Wright, which is if you look at writing integers to some fixed base, like whether it's base 10 or base 2 or some other base g, exactly the analogous theorem holds, that if you look at all numbers that are missing a single digit, the sum of the reciprocals of those numbers converges. And the extension was to this more natural or more general way of looking at integers, where you have this so-called geodetic sequence. And so the theorem for these geodetic sequences is, if, let's say, for every I, you have some finite set of bad integers, bad digits, and you look at all the numbers that have no bad digits, the sum of their reciprocals converges. So if one bad digit kills a number, that's the whole point. Now, just a couple years after Kempner proved his theorem, a mathematician named Frank Irwin generalized it a bit. He said, instead of throwing out every number that has at least one bad digit, you can say, okay, well, if a number has just one bad digit, we'll keep it. We'll only throw out the numbers that have 2 or more bad digits. Or maybe we'll only throw out the numbers that have 3 or more bad digits. Or maybe we'll only throw out numbers that have 1 million bad digits. Of course, these are pretty big numbers. They have to have at least 1 million digits. But you know, after a fairly short time, every number has more than 1 million digits. And if you throw out all the numbers that have 1 million bad digits, you're not throwing out that many in some sense. And so you have a much larger set of numbers, but the sum of their reciprocals converges. So the really interesting extension of this was due to 2 people, Ponomarenko and someone else that I referred to last week. And what they proved was the following. Suppose we look at, let's just put in the context of Kempner's original theorem. So you're looking at the decimal representations of integers. And let's say you're going to throw out numbers, you're only going to throw out numbers which have a huge number of 9s in their decimal representations. And And not so much that, you know, like if they have more than 1 million numbers, you throw them out. I mean, you could have a number with millions and millions and millions and millions of digits. And if you only throw out the ones that have, if you keep the ones that have 1 million digits or up to 1 million digits, you're still throwing out a lot. So the idea was they would say, okay, suppose you throw out all numbers which have, or you only look at numbers which have at most 1% of their digits equal to 9. So if you're looking at numbers which have 1 billion digits, you can keep numbers that have in that billion 10 million nines, 1%. Right? That's the idea. So the number of so your nines are bad digits, but you only throw out the numbers that have, or you throw out the numbers that have more than, like, say, 1% of all their digits equal to 9. Right? A number that has, you know, you can have numbers with arbitrarily many nines, but so long as the nines occur in a number which has, you know, much, you know, 100 times that many digits altogether. So I don't know if that is clear, but that was their theorem. And their proof was probabilistic. They used some probability theory. And so what I'm going to do is show how basically using the same probabilistic argument that they used, you can actually get a much stronger and a much more general result. Now, I suspect many of you are familiar with probability theory. I think of probability as kind of a religion of which I am not a member. So I'm never happy using probability arguments. And back when I used to work with Erdős, he used to think probabilistically. And in stuff we did together, I would spend a lot of time getting rid of all the probability and reducing it to combinatorics and counting. But, and there was only once that I can recall, we actually had a joint paper where I wasn't able to get rid of the probability. Now, in this instance, I also am not able to get rid of the probability, but the probability.
Don't leave us in suspense. What was the one time?
Excuse me?
What was the one time you couldn't get rid of the probability?
Well, if you want, I can send you the paper, but this is, I mean, I can barely remember what I did a month ago. So I remember vaguely what the paper was about. And I mean, it was a problem. It was some combinatorial type problem in additive number theory of the sort we were considering. And
basis of squares?
No. There's something with squares that Joel Spencer, there's something that I had done combinatorially, and Joel Spencer, and I was visiting this guy Spencer at Courant, and I told him what I had just done, and he was able to use some bit of combinatorics that was relatively new at the time and get a much nicer result, a much better result. That I think was published in one of the proceedings of the New York number theory seminar from long ago. In any case, I'm saying this only because I've written down some of the probability that I use because it may be not everyone is familiar with it. And I started with what is the most basic, most simple, and probably most powerful inequality in probability, which is this complete, the elementary thing called Markov's inequality. So now, let's see, gosh. Every now and then there's this ting, and I don't know whether there's someone in the waiting room. I mean, I'm looking at this panel that says, it gives me options like show names of annotators, breakout rooms, whatever. But I cannot find a way to find the waiting room once I have the screen share on. So whoever can't get in, I hope they will tell me at some point, and I will apologize. Okay, so this is the simplest inequality in probability. You have a non-negative random variable, and you know, there's no measure theory here. This is just discrete, countably infinite, if you like, finite probability spaces. And we have this notion of the expected value of a random variable. So the probability that x is at least a is bounded above by the expectation, the expected value of x over a. And then there's this little more curious thing, which gives a lower bound. Interesting. It gives a lower bound for this. That's really the interesting bit. So let's see. So Markov's inequality, you let a, so this is the event. You look at all the elements in the probability space for which the value x of omega is at least a. So this is the definition of expectation. You sum x of omega times the probability of omega over every point in the probability space. And you can break this up into two pieces. The omegas where x is at least 1. X is at least 1. And these are the omegas where x of omega is less than or equal to 1. But x is non-negative. So if I throw away something, I get something smaller. So this is smaller. And x of omega is at least a. So if I replace x of omega by a, I get this, which is equal to this. And then you divide and you get Markov's inequality. Now,
who are the authors that wrote the original probabilistic proof for the?
They're I'll tell you in 1 second. They had a paper called by Brian Luback and Vadim Ponomarenko. I had posted the reference, the bibliography thing last week, so I can do it again. I can tell you, if you send me an email, I can send it to you actually.
All right, thanks.
Okay, now, so this is function e to the x. So you know e to the x is increasing, but e to the minus x is decreasing. So if x is less than a, e to the minus x is bigger than e to the minus a. Or for any positive s, x less than or equal to a is the same as e to the minus sx being greater than or equal to e to the minus sa. And here, it doesn't matter whether x is a positive random variable or not, because e to the minus sx, as we teach students in pre-calculus often, is always positive. So e to the minus sx is a non-negative random variable, and this is a lower bound. So this is Markov's inequality. So we convert this to something that involves this exponential function. Right? So this is, you might say, this is like this brilliant, stupidly elementary trick. And I don't know who is responsible for it, but the person who used it is a guy named Churnoff at MIT. And I'll write down his inequality in a minute. If you have a finite set of independent Bernoulli random variables, so this just means a random variable that only takes on values 0 and 1. So it has value 1 with a probability p and probability 0 with probability 1 minus p. And you let x be this finite sum of Bernoulli random variables. So you have this thing called linearity of expectations. So the expected value of the sum is the sum of the expected values, which is this. So if we let mu be the expected value for x, it's the sum of these p's. And the expected value for e to the minus sx is this expression. And why is it that? Let's see. So I guess I have a proof. So remember, xi is this Bernoulli random variable. It only takes on the values 0 or 1. So e to the minus sx only takes on the value e to the 0 or e to the minus s. And it takes on, so when xi is 1, this is e to the minus s with probability pi. And when xi is 0, this is e to the 0 with probability 1 minus p. And when you add it up, you get this. And again, somewhere they teach you in calculus that 1 plus x is less than e to the x. So 1 plus this is less than or equal to this is the expression. Now there's also one fact, which even I can prove, that if you have a finite set of independent random variables, then the expectation of the product of the random variables is the product of the expectations, when you have independence. So if you have these Bernoulli random variables, x1 up to xk, which are independent, again, it's a straightforward thing to check that these constructed random variables, e to the minus sx1 up to e to the minus sxk, these are also independent. So the expected value of e to the minus sx, remember x is the sum of the xi's. So this is the expected value of this product, which is the product of the expected values, which is, and each of these we have this inequality, is less than or equal to this. So this is e to the si minus 1 times the sum, and the sum of the p's is the mu. So, I mean, there's a reason why I always try to avoid proofs and talks, but I couldn't do it today. Okay. So this is really important. This is what is called Churnoff's inequality. And in some sense, all it uses is Markov's inequality. And Markov's inequality is very general, but because it's very general, it's very weak. And it's amazing that using almost nothing, one gets from Markov's very weak inequality, Churnoff's very strong inequality, which is used a lot, not by me except today, but by people who are probabilists. So in Churnoff's inequality, you start with a finite set of independent Bernoulli random variables, where the random variable xi has probability of success, pi, and so on. And x is the sum, so we know that the expected value of the sum is the sum of the expected values. And this is Churnoff's inequality. It's his lower bound inequality. So the expected value for x is mu. And the probability that x is at most is less than or equal to 1 minus delta times mu. So in some sense, much smaller than the expected value, is bounded above by this. So this can be a very small number. So the probability that x is bounded away from the mean is going to be very small in this case when your random variable is a finite sum of independent Bernoulli variables. And the proof is essentially one line. So I wrote it down. And the proof goes as follows. So the probability that x is less than or equal to this 1 minus delta mu, that was Markov's inequality. We worked this out before. We got this. Yeah, this was Markov's inequality. And I just brought this up on top. And so this is for any positive s. So this, the probability that x is bounded away below from the mean is at most this for any s that's positive. So I want a small upper bound. So I use my calc 1 to minimize this function. And this is minimized when s is minus the log of 1 minus delta. Delta is something between 0 and 1. And in that case, and you also use this estimate for the logarithm, which comes from however you want to prove it. The log of 1 minus delta is bounded above by minus delta squared over 2. I mean, you just need first semester calculus for this. So you just plug these numbers, these estimates, into this. That is, you minimize this by choosing s equal minus the log of 1 minus delta. You approximate the log by this inequality, and this comes out. Right? You get this. This is This is Churnoff's lower bound inequality. So this is when x is 1 minus delta times the mean, the expected value. And a very similar proof also gives you an upper bound, which we don't need. That it gives you a bound for when the probability that your random variable is bounded away above the mean, greater than or equal to 1 plus delta times mu. So yeah, but this is the guy we're going to use. So that's Churnoff's inequality. That's more probability. That's exactly as much probability theory as we need to know. And in this case, you don't need very much to get it. I should go back and say just one thing about Churnoff's inequality. Churnoff actually has a family of inequalities. It's the probability that x is bounded above by like 1 minus delta mu. And this is the case where x is a finite sum of Bernoulli random variables. For other kinds of random variables, Poisson or whatever is your favorite type of random variable, there are corresponding Chernoff inequalities. So this is Chernoff's inequality in this special case. I mean, they're all special cases, but in this special case, when you're looking at a random variable that's a sum of independent Bernoulli variables. Okay. All right, so what does my theorem say? It takes 2 screens to say it. So we're back to the number theory. We have this geodetic sequence, right? But there's a condition on it. So remember the sequence G, it's a strictly increasing sequence of positive integers, and each term GI divides exactly the next term in the sequence. GI divides GI plus 1. So this quotient is an integer. And there's no reason for these quotients to be bounded in general. You have geodetic representations in all cases. But we can only prove this theorem, and maybe the theorem's only true, when these ratios are bounded. So in all the classical cases, they are bounded. I mean, if you take in the classical cases, G sub I is G to the power I. So these successive quotients are a constant. Like for decimal representations, they're always equal to 10. Now, what comes next? So for each I, when you write a number, when you write the geodetic representation, you have a digit between 0 and di minus 1. So I want the ui to be a proper non-empty subset of these. We think of these as the bad digits, the digits we don't want to see. And if we take this average, so ui, it's like some integer, positive integer between 1 and di minus 1. So this is some proper fraction. And if I take this sum of ui over di, and I take the first m of them, and I take the average, I just call that one. So I'm defining d sub m star in this way, right? So that's what this dm star is. And now I choose a number lambda between 0 and 1 over d. This is my d. Okay. I choose a number lambda between 0 and 1 over d. And the set A lambda is going to be all positive integers. So if you take an integer in this interval from gm to g sub m minus 1, so an integer in this interval has a geodetic expansion that looks like this. So it has exactly m digits, and the leading digits, the c sub m minus 1, is not 0, it's strictly positive. If it were 0, it would be too small to fit in this interval. So we're looking at numbers that have exactly m digits. And we want to look at all numbers in this interval. Oh, sorry. So we look at all numbers. So every number is in some interval of this sort, because these integers completely cover the set of positive integers. These are disjoint intervals that cover all the positive integers. And we only look at all the numbers where how many CIs are in these sets UIs? That is, how many bad digits are there? It's no more than lambda times the number of digits. So the cardinality of the set can go to infinity, but if a number is in this set, however many, if it has m digits, at most lambda m of them are bad digits. Right? So this is the theorem. If you look at the sum of the reciprocals of these numbers, this should be an A lambda here, it converges. So first of all, forget the sigma for a moment. The sum of the reciprocals converges. So this is, among other things, a generalization of every theorem we've seen so far, essentially. But it's actually stronger than that, because it's not just that 1 over A converges, but sigma's between 0 and 1. So this is A to a power strictly between 0 and 1. So these numbers, these 1 over A to the 1 minus sigmas, they're bigger than 1 over A. So this is a bigger sequence, but it still converges. So the weaker result would just be, forget the sigma, the sum of the reciprocals converges. But in fact, the sum of 1 over A to the 1 minus sigma converges. Right? So this is So this is interesting. No one ever knows what's important or significant in mathematics, but it's interesting at least. Yeah. So I guess I want to sketch the proof a little bit. And if anyone is seriously interested, or interested even not seriously, in a couple of days I will probably have this written up and posted on archive, so it's easy to find. So remember that my geodetic sequence was the sequence of these numbers, G1, G2, and so forth. The DIs were the partial quotients. G0 is always equal to 1. So GM is the product of all the Ds. And we're only looking at the case where these quotients, D sub I, are bounded by the number D. So this GM is always at most D to the M. Now remember, I had defined this number DM star as this sort of curious harmonic average. And UI is not empty. So UI is at least 1. So I can replace the UI with a 1. And the DI is bounded above by D. So if I replace the DI with the D, I only get something smaller. And if I take 1 over M times M over D, I get 1 over D. So I have this kind of inequality. So this number DM star is also bounded above by D. And IM is just a set of integers with exactly M digits. So they're the digits between GM minus 1 and GM minus 1. And J sub M is all the integers from 0 to G sub M minus 1. So this is all the integers with at most M digits. And this is how many elements are in each of these sets. So if a number is in this set, you can write it as I equals 0 to M minus 1, Ci, Gi. And any one of these numbers, any one of these digits could be 0, right? That's not excluded. The difference between this set and this set is something is an IM minus. I wrote this backwards. But if something, then the numbers that are in the numbers in J, I should have said this is JM minus IM. The numbers that are in JM but not in IM are all the ones with the CM, where this largest digit is 0. So I just wrote this backwards. I need to make a note to myself to fix that. Okay. So JM is the set which has of all integers with at most m digits. And I define this function x of n as the number of digits in n which are bad, which belong to one of these sets u sub I. So x of n counts the number of bad digits in a number. And so a lambda, that's the set that has at most lambda m bad digits if the number has m digits. And so I'm just looking at this a lambda intersect im. So this is now a finite set. And so am lambda, this is all the integers from gm minus 1 to gm minus 1, where the number of bad digits is at most lambda m. And bm lambda is these are the numbers with exactly m digits. These are the numbers with at most m digits. So on this set Jm, all right, let me just remember, Jm is this finite set of integers from 0 up to g sub m minus 1. So the g sub m numbers in that set, and we make it a probability space by giving it the uniform measure where every number has probability 1 over the cardinality of the set. So now x is a function on a measure space, so it's a random variable. And the probability that x is at most lambda m, it's just the number of integers in the set divided in the subset divided by the total number of integers in the set. It's equal to this. So this is the numerator is what we're interested in, and we can write it in terms of some probability. So the numbers in a lambda and in the set im is contained in this bigger interval, is bounded above by this. So what I'm going to do is use Churnoff's inequality to bound this. And I do that by writing my x as a sum of a finite number of independent Bernoulli random variables. And you choose sort of the obvious ones. You, for I going from 0 up to m minus 1, you let xi be the random variable, which only looks at the digit ci in the number n. And xi of n is 1 if ci is bad and 0 if ci is good. So these are the bad ones and these are the good ones. Bad digits, good digits. And the probability that xi is 1, which means the number of integers which have a bad digit in the ith place, is exactly this fraction, cardinality of ui over di. And the probability that xi is 0 is 1 minus this, which is exactly that. So the expected value of this Bernoulli random variable is ui over di. Okay. Oh, now if you pick a sequence of zeros and ones, the probability that xi, so this sequence is this epsilon I, epsilon 0, epsilon 1, and so forth. The probability that xi equals epsilon I for all I is exactly equal to this, which is exactly the product of the probabilities that xi equals epsilon I. That's the definition of independence. So these m random variables are independent. Because they're independent, we can apply Churnoff's inequality to them. Because x, counts the number of bad digits, it's the sum of this finite set of independent Bernoulli random variables. And the expected value of x is the sum of the expected values, it's this, which has this curious expression, which is at least m over d. So apply Churnoff's inequality. See what happens. So lambda dm star is something less than 1. Because the way we picked lambda, we chose lambda to be less than 1 over d, and dm star is bounded above by d. So we have this inequality. So 1 minus lambda d is positive, less than or equal to this. I call this expression delta, and that's less than 1. So 1 minus delta mu this is what goes into Churnoff's inequality, is lambda m. Lambda m is, I mean, mu is m over dm star. This is lambda m. So this probability that x is less than or equal to lambda m is the same in this notation as that x is less than or equal to 1 minus delta times mu. By Churnoff's inequality, that's bounded by this, which is this, which is bounded above by this, because this is a decreasing function, and if I make dm bigger, I make this exponent smaller, so the function only gets bigger. So this is Churnoff's inequality. This is the crux of everything. And it's the crux of everything because d is fixed, lambda is fixed. You know, what can vary here is m. So this is like 1 over something to the power m. We can get a geometric series out of this. So the number of elements in my set A lambda in the interval IM is bounded above by the probability times GM, which is, this is the Churnoff inequality times GM. And now we observe that this number it's e to a positive exponent. So for those of you who have taught too much pre-calculus, I apologize. This is just pre-calculus. This is e to a positive exponent, so this number is bigger than 1. So there's some number sigma positive and small enough so that d to the sigma is less than this. So you choose, there exists a sigma greater than 0 that satisfies this inequality. And so this is the proof. The proof. This is the final thing. So this is what I'm interested in. Remember, A lambda is the set of all positive integers which have no more than a certain proportion of bad digits. So the number of bad digits in A lambda, if the number has m digits, there are at most lambda m bad digits. And I'm looking at this sum of 1 over, it's actually bigger than 1 over a. It's 1 over a to the 1 minus sigma. 1 minus sigma is between 0 and 1. So this is, I can break the set of all integers up into the numbers in these disjoint intervals I sub m that cover the real line, cover the positive real axis. So for m going from 1 to infinity, I look at all the integers in A lambda and this set IM. And this is what I'm summing. Now this is what? It's bounded above by the number of integers in this set, that's the numerator. And in this set, the smallest number is g sub m minus 1. So if I replace each of these by something smaller, I get a bigger fraction, g sub m minus 1 to the 1 minus sigma. And this I bounded with Churnoff's inequality. I got this. And gm over g sub m minus 1, that's just d sub m minus 1. I get this gm minus 1 to the sigma. And gm minus 1 is bounded above by d to the m minus 1. I get this expression. I get, what do I get a geometric series. And how did I choose sigma? I choose sigma, so d sigma is smaller than this. So this fraction is a positive number less than 1. And lo and behold, a geometric series does converge.
Excuse me.
Yes, sir.
dm, when you write dm minus 1, isn't m dependent on the summation? I mean, you can't take dm minus 1 out of the summation. You have to replace it by d.
No. So here, this is d to the sigma.
Wait,
sorry.
what is m? Sorry, what is m? Is m the running index of the summation?
Yes. And this is.
How is it defined outside of the sum?
It's not. I don't. Sorry.
It's not parsing here. I'm sorry.
Yeah. Sorry. I should have wrote. This is d. Dm is d. All the dm's. This should be a d.
And it's not an equality. This is not an equality. Passing from line to line, you need an inequality.
Right. This is right. This is an inequality going in the right direction. This is less than or equal to d times this sum. D is an upper bound for all of these quotients d sub m. So this is less than or equal to d, right? So I have this m minus 1 there. It shouldn't be there. It's less than or equal to d, right? So these are all d's. That's kosher enough. This is d to the m minus 1 sigma. So this is d to the m sigma divided by d. So I have divided by d to the sigma. So I have d divided by d to the sigma gives me d to the 1 minus sigma. Okay. So I apologize for the typos, and I'm really glad you have pointed them out because I would have missed them.
Well, it's just a parsing issue. I mean, you know, it's like the variable inside the
Yeah.
loop and the variable outside the loop. M is invisible outside the summation.
Right. So all I'm saying, right. So this should be less than or equal to d, and that's all I'm using. That's what this is. So this is all legit. This is this number raised to the power m. That's the guy in the denominator. It's this over this raised to the power m. And this is a geometric series, and it converges. So that's my proof. That's good. Now, let me just restate this in a slightly different way. So we have this set A of integers that I just constructed, that this be the characteristic function. And look at this Dirichlet series. So this is a Dirichlet series. And what I just proved is that this series converges for certainly for some real number sigma less than 1. So this series has and it doesn't converge for s equal to 0 because the series A is infinite. The set A is infinite. So this Dirichlet series has an abscisive convergence between 0 and 1. And so this is what in a slightly different language, this is exactly what I proved. And there's an old theorem of Landau that says if you have a Dirichlet series with non-negative coefficients that has a finite abscisive convergence, then at the point sigma of the abscisive convergence, it has a singularity there. And so it would be interesting to know more exactly. All I know is that this abscisive convergence, this sigma c, is between 0 and 1. But I have no decent way to bound it. I certainly have no idea what it is. And if you go back to the original theorem of Kempner from 100+ years ago, what he proved is if you take the set of positive integers that have no 9 in their decimal expansion, then there is some abscisive convergence. It's not just the sum of the reciprocals converges. It's that the sum of 1 over the numbers a to the sigma converges for some sigma between 0 and 1. And it would be nice to have an estimate for that. That is, at the moment at least, an open problem. Another set of open problems is connected with the case of geodetic sequences where you have these unbounded quotients. These gi plus 1 over gi's are unbounded. And yeah. Okay, well, anyway, that is the story du jour. And fortunately, Brian Hopkins is speaking next week, so I don't have to prove a new theorem by next Thursday. Okay, that's the whole story, everybody. Are there any questions? Any?
Yeah, I have a question. So, is there a way to use the other Chernoff's inequality to get conditions where it converges? Or is there some kind of issue with dependence on M or something like that?
I have no idea.
Okay.
You know, this is not something that people have thought about for years. Until today, I don't know if anyone has thought about it, and I've only thought about it for something in the order of minutes or hours. So, no, I mean, so this is an interesting result, but as often happens when you have a kind of like a new topic and you prove something interesting, it just suggests a lot of other related questions, and as often happens, you know, if you have time to think about it, maybe you can solve some and maybe you can't. So there's a story that I'm sure Dick Bumby has heard from me many times. A long, long time ago, I was dean of the graduate school at Rutgers Newark. And at that time, there was there are 3 campuses in the Rutgers system: New Brunswick, Newark, and Camden. And there was a vice president for academic affairs over the whole system, a physicist named Alex Pond. And before anyone got promoted, it went through a whole series of steps of people looking at these promotion dossiers. And the final guy to make a decision was Alex Pond. And one day he said to me, you know, why is it that whenever the math department puts someone up for promotion, tenure, whatever, the letters of recommendation always say, this guy is one of the best 10 guys in the world in his field? And I said, it's very simple. That in physics, you're a physicist. In physics, there are a small number of problems and everybody works on them. In mathematics, there are a lot of problems. So in any given problem, maybe only 10 people are working on it. And if you're one of the 10 best people in the field, well, that's not hard to be. So, so that's sort of the situation here. It's like you can be one of the top 10 people in the world in studying these geodetic digit problems. And since there are less than 10 people in the world who have seen this stuff so far or thought about it, you'll be one of the world's leaders. What the hell? It's, grab the opportunity. Okay. Wow. All right. So if there are no other questions, I will see you all perhaps in a week, except maybe for Shreya Hegde, who I promised to talk to after the talk if she's available.
All right, take care.
All right. Bye, everybody.
Many thanks.
Thank you.
Thank you. Bye.
Thanks for this, Nathanson. Thanks for the talk.
Sure.
Okay.